Der nächste Teil geht darum, um eben diese neuen Startups, diese neuen Ideen an den Markt zu bringen. Dazu braucht es eine neue Generation oder auch die nächste Generation an Ingenieuren, Wissenschaftlern und Technikern. Und National Instruments hat sich seit jeher auf die Fahne geschrieben, auch da mitzuwirken und das mitzugestalten, um mitzuhelfen, die jungen Leute zu faszinieren für Innovation, Technik und das Ingenieurwesen. Und ich glaube, es gibt keinen besseren Botschafter bei National Instruments, keinen enthusiastischen Botschafter für diesen Bereich der Ausbildung als mein Kollege Dave Wilson. Welcome on stage, Dave. Welcome back to Switzerland. It's great to have you.
Great to see you.
Good to see you.
Well, today's students are tomorrow's innovators, and we need to prepare them with the tools of discovery so that when they graduate, they will make an exponential impact on our world. These students will design the complex systems that Christian spoke of. But as we know, systems are getting more and more complex all the time. A really good example of this is seen in the area of time itself, right here in Switzerland, where watches were created and perfected. Our early timepieces had hands and springs and gears, and they would tell you the time. Some of these evolved all the way up to the point where they would tell you the date as well. But we know that our new timepieces are significantly more complex and sophisticated. In fact, they'll tell you the date, they'll tell you the time, they'll tell you if you have email, they'll monitor your heart rate, they'll monitor what you eat, and tell you a little bit about yourself and how you're doing over time. They may tell you if it's a good idea to eat that next piece of Swiss chocolate or not. They're significantly more complex, and yet they're the starting point for today's students. Another good example is seen in the area of transportation. Now, our early vehicles had internal combustion engines, burning gasoline, emitting carbon, but they would get you from point A to point B most of the time. But our new systems of transportation, significantly more complex. These are things like the Tesla Model S or the BMW Model i3. They feature aluminum chassis, electric motors, hundreds of ECUs, hundreds of sensors, significantly more complex, and yet the starting point for today's students, the very starting point for them. So in the early days, when students were learning how to design those early systems, they would write equations that would scale pretty closely to the basic functions of those cars, the basic things. So it's a really good thing that the blackboard with white chalk evolved up to the whiteboard with black markers to accommodate all this added complexity for students. Well, we know there's a better way. And we know that when students can do engineering, at the moment that the concept is introduced to them, they move beyond just the theory and the equations to seeing these as tools that they will put together to create the new systems that they will design and that you and I will drive. This is where the students are finding excitement in engineering. So what does it take to become an engineer? What does it take to move through the path of a student? Well, if you take a look when a student sits down from the early days and they use something like Lego Mindstorms, they're connecting the blocks to make things work. This very technique scales all the way up to science and engineering. So what does it take then? Well, we know that practice makes perfect in everything, including becoming a scientist or engineer. So what you have to have is something that maintains its approach and its consistency so that you can practice it over and over again to become a scientist or engineer. Well, that consistency of methodology in science and engineering is something that we call LabVIEW. From the moment a student connects the blocks to make things work in Lego Mindstorm, this approach scales all the way up to everything that we do commonly as a group here in designing our systems. So we're very excited about that commonality and consistency. So when we start them with students, we take them on their first step, and we want to put things in their hands that will allow them to experience things. How can we then show them authenticity and make things work? Now, a really good example is seen in the area of wind turbines. This amazing structure will inspire many questions from students, like how fast does it turn? How powerful is it? Will it power a house? Will it power a whole city? What is the answer to that? We could just tell them the answers to these questions, ask them to memorize those answers, and expect them to design things in the future. But we thought it would be better to be able to take that authenticity and let them discover the answers for themselves. So we've been working on a program that we call Mini Systems that takes as much of the authenticity as we can and reduces these down to the size of things that we can put in the students' hands. And working with teachers and working with professors, we've developed some things that students can put in their hands and actually experience things in operating conditions. Things like vertical takeoff and landing, so you could discover how PID works and how cruise control actually operates. Or how about a shaker table, something that actually moves the building back and forth, as opposed to building the small building and putting a large book on top of it to see if it can handle the weight. Well, that's not what happens when an earthquake happens. The ground actually moves. Well, the students can experience that now because this is something that they can do at the moment that they're learning about things like S-waves and sinusoidal functions. Roll chassis dynamometers. How does that actually operate? How much power is in a battery? What kind of horsepower does this little motor actually deliver? We could tell them the answer. We would prefer that they actually try it out and discover that for themselves. So we've been working, and we're excited to say that through LEGO Mindstorms and through this program, many students will be affected. We're working with many institutions like Tufts, Southern Regional Education Board, PITSCO, Project Lead the Way, to produce and make these available. And in the end, we believe that over 4 million future system designers will be inspired to join you and help you design and build the things that you're doing right now and all the endeavors of engineering and science. So we're very excited about this. As we take the next step in a student's education, we go off to university where it's even more exciting to see the theory come to life. This is when you begin to actually make gears and deploy the control system algorithms, understanding how the math actually functions. And we needed a device that could actually deliver this. So this time last year, we announced something called MyRio, which I think has some of the best technologies that we could squeeze into a small box and put in the hands of the student. And it's been an amazing year with real-time, determinism, all of LabVIEW, mathematics, over 58 points of I/O in the box. We've got a device that the students can actually use. And it's been an amazing year. Over 60 countries now are using the device. Almost 1,000 universities are using it. 20,000 students are doing engineering, and we actually have new applications up on the LabVIEW Tools network. So it's been a very exciting time, and students are actually out making things work. And as exciting as this product is, we're more excited about the applications the students are doing with it. Things like painting your silhouette with a paintball gun. And I'm telling you, if it's your silhouette that they're painting, it's very exciting. It's very exciting, especially when you're trying to tune it and calibrate it to the perfect silhouette. You may be glad you didn't eat that last piece of chocolate at that moment in time. And even basic robotics to complex movements and functions. These are the works of students, things that are really inspiring us. And we have something called the Student Design Competition that recognizes this work. Students from around the world, over 3,250 teams were involved in this competition. You can imagine all of the work done. 25 different countries, and we had the fun but the arduous task of only selecting 3 finalists, and I'd like to tell you just a little bit about the finalists. So our first finalist was something called the NASA Student Launch Project, and this came from the US. It came from the University of North Carolina in Charlotte. And these students built a rocket. They were inspired by things like thrust modulation and thrust vectoring, right? And they actually built a rocket, they put MyRio in and they launched it. Perfect trajectories every single time. And on the way down, they were able to survey the landing spot to make sure that it was clear. They were able to do this. Another really great example came from the Korea Advanced Institute of Science and Technology. Now, these students were inspired by the autonomous vehicles that are running around, and they wanted to do this now instead of waiting 5 or 6 or 10 years to get their chance when they went to industry. So they built their control system, they put it in one of the brave students' own cars, and they navigated through the city streets and were able to actually do perfect path planning and do that engineering that they were so inspired at the moment they were learning the algorithms like path planning and mapping. Very exciting. So out of all of these three, though, there was one that came out on top of the world. 3,250 teams, and one team won everything. And that came from right here in Switzerland. ETH Zurich and Team CPOs built a robot, an underwater autonomous robot that inspired us all. It inspired us at National Instruments, but every other educator and robotics team looked at that and they said, wow, that's innovation. And I'm proud to tell you that that came from right here in Switzerland. So let's take a look at the video and see how this came together. So you can see that biomimicry, of course, is important, and we learn a lot from it. But as you can see in their robot, they were able to take the concepts and deploy these concepts in something that was maybe obvious in the fact that it could move, but now multi-dimensionally. So very exciting. And they talk about this control system that when it goes down on the seabed, well, guess what? There's seaweed down there. You know, I've seen it myself. Rotational propulsional systems get tangled up in the seaweed, right? Not with CPOs. CPOs was innovative in solving that problem. So to give you an idea of the kind of things that are happening and that innovation from right here in Switzerland, but instead of me telling you everything about it, I'd like to invite up the students who are here, Martin and Vincent, and tell us a little bit about your application.
Thank you, Dave.
Gentlemen, welcome. Thank you. Welcome. Guys, this has been so inspiring, and as I had mentioned, everybody in the world that we've shown this to, and we've shown a lot of people, believe me, we're very excited and inspired. So can you tell us a little bit about the technicality behind the robot?
Ja, also der Roboter besteht aus einem langen Tauchzylinder, an den 4 Flossen befestigt sind. Im Tauchzylinder selber haben wir die Batterie, eine Kamera, ein Laser, eine IMU mit 10 Sensoren, 2 Feuchtigkeitssensoren, eine Schwimmblase mit einem Motor und natürlich den Mario. In jeder dieser Flossen haben wir 9 Servomotoren, die wir einzeln ansteuern können. Wir haben also insgesamt 37 Motoren und etliche Sensoren. Das heißt, der Mario, der drin ist, der hat einiges zu tun.
Well, very exciting, very innovative. I saw you guys when you were building this, and they told me they had to finish it before the end of the semester. You see, they have real deadlines. They couldn't slip or they couldn't graduate. That's how it works, you know, at university. But you must have had a design process then that you were confident was going to get you to such a successful robot. Can you tell us about the design process?
Nun Dave, wenn man ein Jahr Zeit hat für ein Projekt wie dieses, dann möchte man natürlich so schnell wie möglich Versuche in der Praxis durchführen. Und hier auf dem Bild sieht man unseren ersten Prototypen bestehend aus einem Stofffetzen, einer Sperrholzplatte und ein paar NXT-Controllern. Das war nach der ersten Woche und so sollten wir mal sehen, ob das physikalische Prinzip überhaupt funktioniert. Ein Kollege machte sich daran, die Programmierung in C zu implementieren, doch hatte da gewisse Schwierigkeiten bei, bis ein anderer Kollege LabVIEW als Alternative vorschlug. Und nach nur einem Tag konnten wir diesen ersten Test starten und nach kurzer Zeit jede beliebige periodische Funktion mit unserer Flosse nachvollziehen. Und dann ein halbes Jahr später, als wir unsere Hardware für den fertigen Roboter beisammen hatten, waren nur 3 Wochen der Programmierung nötig und wir konnten zu unserem ersten Tauchtest übergehen.
So such an exciting robot. And we know when you do engineering, the real magic is when you can see it and touch it and feel it. So I think you have the robot here, is that right?
Ja, unser Roboter kann drüben in der Expo gesehen werden und wir beantworten auch gerne sämtliche Fragen.
Well, gentlemen, thank you. Make sure you take a look at their wonderful robot, and thank you so much for your great work. Thank you.
Danke gleichfalls.
So all of this work is being done to prepare students to come out into the world and work with you to build systems that make a difference in our world. And we feel really good that by putting these great technologies in the student hands, the evidence is that amazing and wonderful things will happen. It's just obvious. So we'll work to do our part to make sure we keep creating those technologies, and then we just have to sit back and watch the magic happen as our wonderful professors and our students get out there and make all the work happen. So preparing people for industry is what we're doing, and Asa Kirby and Daniel Riedelbaugh will come and tell us all the great things that are happening out there in industry.